Okay, good morning, ladies and gentlemen. I'm Darryl Lee, the Consortium Manager for ROS Industry Asia Pacific. And together with me, I have Glenn Tan, one of our talented development engineer in the team. So I will be sharing on some of the Asia Pacific updates. And Glenn will be sharing on insights of his development work on easy robotic vision and manipulations. So for those who are still unaware about ROS Asia Pacific, actually we are situated in Singapore and we are being managed by Advanced Remanufacturing Technological Center, ARTC. It is a research arm of the Agency for Science, Technology and Research, A-STAR, which is a statutory board of Singapore government that performs R&D to support the competitive advantage and national needs of Singapore. So coming back to ARTC, we are here, or rather ARTC is here is to function as a private-public partnership and framework, translating research and development solutions to the industry. So ARTC mainly focusing on advanced manufacturing and remanufacturing capabilities and capture values through implementation of solutions with industries. So under the technological readiness level of TRL, in Singapore, TRL 1 to 3 is taken care by the Institute of Higher Learning, namely the polytechnics and the universities. ARTC sits between 4 to 7. They are actually there to address the value of depth in innovation. So ARTC focuses in process validation, optimization, conceptualization of technologies, and lastly, to deliver solutions to address industry needs. So next up, I'd like to maybe give an introduction about Focus Technical Project FTPs, for those that are still not really aware about this. So FTPs are used to drive members' needs by co-development and creating new ROS-based platform technologies and enablers. So it can be achieved by lowering the required investment by cost sharing between members. And the solution developed will be contributed back to the open source community. And this allowed members to steer the direction of the de facto standardization of ROS. It helps to accelerate the organic growth of ROS platform development through faster creation of future open source capabilities made by others, and while it's being leveraged back by the consortium members free of charge to create future solutions. This helps in proliferating ROS platform component in order to achieve industrial grade quality faster and quicker for adoption. So recently, we have went through a FTP roadmap generation through the use of a survey. And the survey is to elicit the common problem statement that and needs from members to craft out work streams of future FTP topics, where co-development between members can take place. And I will be sharing more about this in the later slides. So we have an upcoming FTP in Interoperable Robotics with RMF. And for those not very familiar, RMF stands for Robotic Middleware Framework. So RMF is an integration framework that will enable many different and complex technology systems to communicate and interoperate with each other. It allows the management of robot fleet and to manage robot traffic communication to building infrastructure, such as doors, lifts, and among others. So in Singapore, RMF has been deployed in hospital, and we would like to use this FTP to translate towards a solution that is really commercialized for manufacturing industry. By working with our members who are industrial partners, we are looking to deliver a fully autonomous operation solution, which is also scalable as well. So our objective of this RMF FTP is to expand RMF with generic sensor interfacing and to enhance capabilities in RMF for manufacturing and warehousing use cases. And lastly, to provide a physical test bedding of RMF for our member access and interoperability testing. Currently, we are looking to launch it in the mid of this year, possibly in May or June. So, as communicated earlier in the previous slide, early this year, we have performed a survey to elicit the common problem statement and challenges in robotic, industrial robotic application for us to find synergy on potential FTP roadmap creation. So we have 15 of our consortium members participated. And in summary, based on the result, interoperability in RMF has the highest vote. And since FTP has been set in place, we actually identified that mobile manipulation could be the next FTP topic. So the survey also showed insights on the challenges faced when deploying robotics robotic solution in industrial application. So some of the challenges are high hardware costs and complexity in setting up sensor fusion, so on and so forth. So this may be taken into consideration when we curate future FTPs. So we can look at greater details in the following slides. So we have separated the robotic challenges into different applications, namely the machine vision, robotic, the usage of robotic arms, the usefulness of simulation, and as well as mobile manipulation. So for the challenge of usage in machine vision, the most prominent issue faced actually is the setup of complex sensor fusion to achieve useful performance. And this usually results in higher hardware costs and longer setup time. So for the challenges when industry application of robotic arms, we found that it revolves mostly around the absence of good dynamic safety capabilities, as well as it is hard to achieve desired performance outcome when deploying such a system. So in challenges in leveraging simulation tests, we found that due to reliability gaps, complex simulators, and difficulty in replicating environment constructions, this often results in limited test scenarios and thus hindering the full benefits of having such a simulation. And lastly, in autonomous mobile robot and autonomous guided vehicle, when we deploying them, we find that it is complicated to achieve the desired reliability, as well as security-related issues such as tailgating and remote hacking, and just to name a few. So based on this, we conclude that we have found some of these insights that we will take into consideration when we start to work with our industry members on FTP topics. So next up, I'd like to share some updates on ROS-I AP training. So a 3-day course was curated and delivered to ROS Industrial Consortium members. The training package includes ROS-I AP basics and the application of easy perception deployment, namely EPD, and easy manipulation deployment, which is EMD. So Glenn will explain a little bit more about this in his slide later. So we are looking at this training workshop to be open to the public in the quarter of this year. So maybe some explanation on this. It's for easy perception deployment, EPD. We are looking at package that take care of object detection, classification, tracking, and accurate positioning modules. So for easy manipulation deployment, we are looking at flexible, fast grasping library for multiple types of manufacturers, and especially with integrated collision avoidance capability. So we have conducted this training with 30 participants from 7 companies, and we have provided them with in-depth technical explanation for each of the working principle for each package. So we also took the opportunity to acquire valuable feedback from them when they are deploying their robotic solution, and some of the potential use case that we have identified is mobile manipulators, depalletizing, easy pick and place configuration setup in manufacturing sites and as well as FMCG warehouses. So yeah, so with this, I would like to pass on to Glenn to share more about his developmental work on easy robotic vision manipulation using EPD and EMD. Glenn?
Thank you, Daryl. Can you hear me?
Yes, yes.
Okay, so next I'll be providing some updates on the easy perception deployment as well as the easy manipulation deployment ROS2 packages. So the easy perception deployment package is a ROS2 package that the team here at ROS-I Asia Pacific has been working on that accelerates the training and the deployment of custom trained computer vision model for industries. Next slide, please. Okay, some of the features that EPD includes permissive licensing, which allows for commercial solutions to be built off it with minimized legal complications. Training and deployment time is also reduced with transfer learning. As this is a ROS2 package that is specifically targeted at users with no programming background, configuration and running of this package is done using a graphical user interface. Lastly, EPD also utilizes the ONNX model format that prevents machine learning framework lock-in, especially when different frameworks provide different models that cater to different use cases. So there are 2 main workflows for EPD. First is the model training, second is model deployment. The user can first train their model to detect specific visual objects using a simple input of a folder of training images and a text file containing the object classes the model needs to detect, which will then generate a train ONNX model file. Next, using this trained model, together with the previous class label list, the user can then deploy this trained model as a ROS2 package. So to meet most of the computer vision needs, EPD is thus able to provide object classification and localization in the form of a custom ROS2 messages, which can then be used in other packages that might need to harness such information, one of which is the easy manipulation deployment package that we will talk about later in a few slides. So EPD is also highly customizable with 3 precision levels that each has its own trade-offs, but is also useful for tailoring to your specific needs. The precision level determines the speed as well as the level of detail of computer vision provided. As you can see in the table, precisions can be set from the lowest precision of 1, where the model only identifies the presence and identity of objects in the scene, to precision level 2, which provides the bounding box, and lastly, providing the segmented image mask of the detected objects in the scene. In particular, for robotic tasks, the precision level 3 has been identified to be the most commonly selected level due to the amount of detail provided in the output. Beta testing of the Easy Perception deployment package has already started on commercial industrial projects, like what you see here. Using the precision level 3 object localization use case and operating at 2 frames per second on the mid-tier NVIDIA GPU, we were able to verify EPD's use for an industrial conveyor tracking and automated picking task in ROS2 Foxy. So next, we'll look at the Easy Manipulation Deployment ROS2 package. So this package aims to provide a user-friendly, modular, and configurable manipulation pipeline for pick-and-place tasks. So the EMD consists of 3 main features: the Workcell Builder, which facilitates the generation of a pick-and-place scene representation; the Grass Planner, which is a highly modular and flexible planner that provides the optimal end effector pose to grasp an object, as well as a grass execution component that currently uses Move It to navigate to the pick object, while dynamically accounting for safety. Each of these components aim to reduce the steep learning curve that new users to both programming and ROS may face when integrating an automatic pick and place system into their tasks. So for the Workcell Builder portion of EMD, it is meant to provide an easy way to create a simple pick and place scene. This is done through automatic generation of pick and place workcell description packages, complete with the combined URDF and SRDF of the manipulator and end effector, as well as creating simple static object description packages. These features are provided in a way that is easy to understand using a graphical user interface, which adheres to the URDF format provided by the documentation, while removing the need for users to understand the syntax and the location of where to put certain files inside the workspace. For the grass planner itself, it was designed to provide an alternative to deep learning grass planning approaches, which, while accurate, requires users to label huge amount of data to increase its accuracy, especially for unique objects, which existing datasets may not be comprehensive enough to cover. Furthermore, these existing datasets are limited to two-finger representation of a specific width, which also creates another problem of having to relabel data with different representation depending on the dimensions and the type of end effectors that are being used. So this grass planner will aim to address this by providing an algorithmic depth-based approach that uses point cloud information to determine the grass poses, while at the same time accounting for finger collision as well as stability. This helps to eliminate any need for training of object data at all and makes it a lot easier to switch between end effectors for different pick and place situations. So as you can see, these are some of the grass plans that are generated by the EMD grass planner. For finger grippers, the grass planner first does finger collision checking for the gripper in its open configuration using the flexible collision library to ensure that the gripper does not collide with the environment. Next, gripper contact point ranking is done, where the contact points of each of the fingers would then be passed through a ranking algorithm to determine the quality of grasp with attributes such as surface curvature, antipodal grasp angles, as well as distance from the centroid of objects. For the suction gripper, a similar ranking algorithm is used as well, with the additional attribute of surface contact points. So these end effector grass plans generated can be easily switched between each other using a very simple configuration file that we will look at in the next slide. So as you can see, this is the configuration file for both the finger and suction cup grippers. So the configuration files are in the YAML format for easy readability and ease of use for new users. Multiple end effector configurations can also be appended into an array, and grass plans for all of these end effectors will be generated and ranked accordingly. This approach is significantly easier than changing end effector grass plans for deep learning based grass planners, where users will need to generate end effector specific labeled datasets for each of their use cases. So lastly, we look at a grass execution component, which involves integrating dynamic collision checking during trajectory execution, which is currently demonstrated with the scenario as shown, where the moving collision object enters the pick and place scene and it's simulated by a remote jogging of one of the robot arms. So the dynamic collision checking can be split into 4 different steps. So first, the joint state of the arms are updated, then the future states of the collision object based on its current trajectory is calculated to check if there's any point of collision between the collision object and the picking robot's trajectory. Next, depending on where the collision occurs with respect to the picking robot trajectory, the picking robot will then react based on the safety zone that we have designed, which we will explain in the next slide. So the way the grass execution component reacts to a new collision object detected in the scene depends on the part of the safety zone where the collision is detected. It is considered to be in the blind zone if the collision is detected too near to the robot, such that a complete collision check cannot even be completed. For the emergency zone, it is defined when a collision detection occurs somewhere after the first collision check iteration, but is still not far away enough such that there is enough time to slow down and stop safely. When collision is detected inside both the blind and the emergency zone, the robot will stop immediately. The next two zones, the slowdown and the replan zone, as well as the dynamic replan zone, allows for the robot to continue its trajectory while doing replanning. But depending on how far ahead the collision is, the robot may or may not slow down the current trajectory during the replanning action. So these are some of the examples of how the dynamic safety component works in simulation, specifically demonstrating the replanning capabilities. An additional thing to note in the middle example is that replanning will be re-triggered even if the first replan does not work. Various dynamic safety parameters required for these operations will also be abstracted out and provided as a highly modular component to allow users to easily add this module in their pick and place task easily. So if there are any other inquiries on the features or issues for either of the packages, do reach out to us at the following contact details. Thank you.